Hello everyone, thank you for attending our talk on penalizing small errors using adaptive logarithmic loss. This work is a joint collaboration with Nick Pierce, Hang Dai, Roderick Murray Smith, and Suresh Manandhar. Fundamentally, loss functions define a functional landscape for traversal by gradient descent. Although numerous loss functions have been proposed to date in order to handle various machine learning problems, little attention has been given to enhancing these functions to better traverse the loss landscape. In this paper, we simultaneously and significantly mitigate two prominent problems in medical image segmentation, namely class imbalance between foreground and background pixels and poor loss function convergence. To this end, we propose an adaptive logarithmic loss function. The plot here shows the value of the derivative of our loss against the value of the dice loss that it optimizes. The loss has a smooth and almost linear response below a particular empirically set threshold, following which it has a nonlinear response, penalizing errors more drastically. It can be seen that for smaller values of the loss metric, a larger loss is being backpropagated. Gamma is fixed empirically based on initial experiments to any value on the x-axis. We constructed a loss function that can both converge at a faster rate as well as adaptively refine its landscape when closer to convergence. The formula for this adaptive loss is shown in the slide on the left. C here is used to make the loss smooth and differentiable at the point of discontinuity, that is, modulus of the dice loss equal to gamma. dl is the computed dice loss. Gamma, omega, and epsilon are the hyperparameters. As the value of the dice loss lies between 0 and 1, we experiment with values of gamma that are between 0 and 1 to find the optimal threshold to shift to the smoother log-based loss for convergence closer to the minima. This works well as log is a monotonic function and hence it smoothens the convergence landscape. We observed negligible computational overhead compared to other loss functions for computing our loss. The optimal values for the hyperparameters are reported in the paper. The loss is mainly sensitive to the values of gamma, while epsilon and omega can be kept constant, as we observed little change in the value of the loss across these two parameters once they had been optimally set. We applied a grid search strategy to find the optimal hyperparameters for our loss, where we first ran some initial tests to see the behavior of the loss given some values of the hyperparameters and then tuned them. Initially, we set the value of gamma as 0.1 and tuned the values of omega and epsilon to the optimal settings. We then used the empirically estimated omega and epsilon to find the optimal value for gamma. The values obtained are shown in the tables on the right. We can see here that the loss isn't affected a lot by changes in epsilon and omega, but even a small change in gamma can cause significant changes in the loss value. The experiments for our methodology are conducted with two architectures. We use the benchmark UNet and the attention-based focus net. Further details on the architectures can be found in the paper. We use three datasets that exhibit varying class imbalance for our experiments: the ISIC 2018 skin cancer dataset, the Data Science Bowl 2018 cell nuclei segmentation dataset, and the Drive retinal vessel segmentation dataset. Preprocessing and further details about the datasets are given in the paper. To keep the evaluation fair, we do not use any augmentation strategies, as different augmentations can affect performances differently. We compare the performance of our loss with various state-of-the-art losses such as the combo loss and the focal loss. The ISIC 2018 dataset shows the least imbalance, and hence the results are fairly even for this dataset, even though our loss does manage to get the best-in-class Jaccard index. We also compared FocusNet, trained with the adaptive logarithmic loss, against the recently proposed focal Tarvisky loss for the ISIC 2018 dataset. We used the same training and testing splits as their implementation and averaged our results over 3 runs. Our loss outperforms their architecture trained on their loss by 1.53% on the DICE index. We also reported a better precision and recall than their methodology. The nuclei segmentation dataset exhibits more class imbalance, and in such a case, our loss shows significantly superior performance compared to all other losses. FocusNet with just the DICE loss suffers from poor convergence and does not get competitive results on this dataset. We do not compare the Drive dataset by the area under the receiver operating characteristics curve or the accuracy, as these metrics are fairly saturated for this dataset, and do not offer any statistically significant insights. It is interesting, however, to note that we do get an improved F-measure score and the best-in-class intersection over union, given the large number of batches extracted, which is statistically significant. Overall, our loss significantly improves performance over the baseline dice loss for all three datasets. Here we can see the ROC curves for the skin cancer segmentation dataset and the data science bowl dataset. When it can be seen when the imbalance in the pixels is high, our loss provides a much more robust and significant AUC ROC than the baseline, demonstrating a superior convergence. The curves shown here are plotted for the best performing models from our experiments. In all cases, the trend shown by a loss is to converge to within a delta of the optimal solution and then refine the convergence using the adaptive strategy. Without the adaptive strategy, a loss often gets stuck in a local minimum, which reiterates the importance of having such a piecewise continuous loss function. The other loss functions exhibit slightly unstable convergence. We observed that our loss mostly converged faster than the Jacquard loss, the dice loss, the Tversky loss, as well as the combo loss. The convergence of the focal loss is at par with our loss, while the Tversky loss converges more smoothly. The plots for all the losses against the EPOCHS are shown in this slide. Further details about our loss are available in the paper. Thank you for taking the time to view this presentation.